Section 4.1, we're learning about related rates. Most of the time, changing quantities don't change alone. So if we know that there are two related quantities that change over time, the rates that those quantities change are related. We're going to solve problems like that in this section. Let's start by talking about a balloon example. So imagine that you are filling a balloon with air using some kind of helium tank, for example. As the helium tank is pumping helium into the balloon, you'll notice that the balloon gets bigger and bigger and bigger. So as time goes on, the helium is pumping into the balloon, increasing the volume of the balloon. And when the volume of the balloon increases, the balloon's larger, we can also see the radius is increasing. We know that the rate that things change are represented with derivatives. So when we say the volume is changing over time, we'll use the derivative dv dt to represent that. And when we say that the radius is changing over time, we'll use the derivative dr dt to represent that. In this section, we'll solve related rates problems, and there's 5 steps that the book outlines for us. The first step, assign symbols to all variables involved in the problem. I recommend writing out each of the things that change over time, and then to write next to that the symbols that you're going to use to represent those changing quantities. Step 2, you're going to state in terms of the variables all the information that's given to you, as well as which rate we're looking for. In most cases, there will be 2 related quantities. One of them will be given to you. The other one you will be looking for. Step 3, we're going to find an equation that relates the variables from step 1. Step 4, using the chain rule. This is super important. If you forget the chain rule part, you will be lost. So using the chain rule, we'll differentiate both sides of the equation with respect to the independent variable. That resulting equation will relate the derivatives. So that equation in step 4, that's the related rates equation. From here, we'll move on to step 5, plugging in all the known values and then solving for that unknown rate of change. So let's see an example. Going back to our inflating a balloon, we're told that the balloon is spherical and that it's being filled with a constant rate of 2 cubic centimeters per second. And then we're asked how fast the radius is increasing. The radius is increasing when it's at exactly 3 centimeters. So this is an instantaneous rate of change. We don't want to know how the radius is changing the entire time or the average change. We want to know exactly how fast is it increasing at that 3 centimeter mark. So let's use our 5 steps. Step 1, let's identify the variables. We have volume, radius, and we have time. Volume changes over time, so to create a symbol that says that, I'm going to say volume is a function of time. Radius also changes over time, so I'll say radius is a function of time. And then time, that's our independent variable. So I'm just going to say time is t. So we have our 3 symbols, v of t, r of t, t. We know that volume changes over time, so we can represent that rate of change as dv dt. We know that the radius changes over time, so we can represent that rate as dr dt. So volume rate of change, I'm going to put ROT for that, and this is radius rate of, not T, that should be ROC, rate of change. There we go. All right, step 1, assign symbols to all of our variables. Done. Step 2, we're going to state in terms of these variables the information that is given. So we know that the volume is changing. We're filling the balloon with air at a rate of 2 cubic centimeters per second. So the amount of volume change, that dV dt, is 2 cubic centimeters per second. And then we're asked to determine how the radius is changing. So we're looking for dr dt when r is equal to 3. That's all the given information. So given, and then what we want to determine. Let's move on to step 3, which says to find an equation that relates the variables in step 1. The only thing I can think of is that volume is equal to 4/3 pi times radius cubed. And since radius is a function of time, I'm going to rewrite this r cubed as parentheses r of t cubed so that we can remember both volume and radius are a function of time. And then we're ready to move on to step 4. Step 4 says to take the derivative with respect to our independent variable, which is time. So we will take the derivative of both sides with respect to time. And step 4 says to use the chain rule, and this is super important because if we forget to use the chain rule, we won't get the related rates that we're looking for. So let's work out this derivative right here. On the left, the derivative with respect to time of volume, a function of time, that would just look like dv dt. On the right, I have the 4/3 pi constant multiplier outside of the derivative, since we know we can factor that out. And then we need to multiply to the derivative of radius, a function of time. But this is radius cubed, which means we're going to have to use the chain rule to do the derivative first with respect to radius of r cubed. And then after that, we'll multiply by the derivative of radius with respect to time. So this is the chain rule part that is mentioned in step 4. If we didn't do the chain rule here, we would not find that dr dt value. Let's go ahead and carry this equation down. The derivative of r cubed with respect to r, that looks like 3r squared, and then multiply that by dr dt. This is our related rates equation. Double check in step 4 that you have 2 different rates inside of your related rates equation. That's the whole point of step 4, is to find an equation where you can have both derivatives appear. If you don't have 2 derivatives in there, there's a good chance that you did not use the chain rule in step 4 when taking the derivatives. Okay, that's it for step 4. Let's move on to step 5, which says substitute in all known values. Well, we have a few known, well, 2 known values technically. We know that dV dt is equal to 2 cubic centimeters per second. So we'll plug that in to dV dt on the left side of the equation. And then we know that we're looking for dr dt, when r equals 3. And so we're going to plug in r equals 3 on the right side of the equation, and then we will solve for dr dt. So our related rates equation becomes 2 cubic centimeters per second is equal to 4/3 pi times 3 times r squared. Using r equals to 3, that becomes 3 squared, times the dr dt that we're looking for. We can simplify this a tad bit. I see that we have a 4/3 as well as a multiple of 3. So let's reduce this factor of 3 with this one. And then 3 squared, that's going to become 9. So we'll have 4 times 9 on the right-hand side of our equation, which is 36 times pi times dr dt. That's our right-hand side, simplified. And on the left, we just have the 2 centimeter cubed per second. Ooh, and I did notice that we don't have our units written out on the right-hand side of the equation. If we think back to r is measured in centimeters. So when we did r cubed, that becomes centimeters cubed. So on the right-hand side of our equation, we are looking at cubic centimeters. But then when we took our derivative of left and right-hand side, that became r squared. So right here in the r squared, we're looking at square centimeters. So this 36 pi, that's actually square centimeters. And then dr dt, that's a centimeter changing per second, so that looks like centimeter per second. So the units on the left and the right-hand side of our equation actually match out perfectly. We have centimeters squared times centimeter. That's centimeter cubed, just like the left-hand side, and then per second, just like the left-hand side. All right, going back to solving our equation, we are looking to isolate the dr dt. So we just need to divide by 36 pi on both sides. Which leaves us with 1 over 18 pi. And we had divided off 36 pi, which came with the centimeter squared. So we have centimeter cubed per second divided by centimeter squared. That reduces us down to centimeter per second. So we have dr dt is equal to 1 over 18 pi centimeters per second. And that's only true at the value where the radius is equal to 3 centimeters. So how fast is the radius increasing when the radius is 3 centimeters? It's increasing at 1 over 18 pi centimeters per second. And that's an example of a related rates problem. I'm going to break these up into separate videos. That way you can watch one at a time. These problems can feel very lengthy, so take your time with them. Read through the section, watch the video, try it on your own. Also, I'd like to encourage you to try the extra problems throughout the section. After each example that I work through with you, I'd like you to try the one after that, make sure that you're getting the correct answer, and remember that those answers are posted in the online PDF version of your textbook. All right, see you in the next video.